Hello everyone, my name is Zhang Qingyue. Today, my topic is about measurable sets. At first, let's look at the definition. A subset E of Rn is said to be Lagrange measurable, or simply measurable, if given epsilon larger than zero and there exists an open set G such that E belongs to G and the outer measure of E minus G minus E is less than epsilon. And if E is measurable, its outer measure is called its Lagrange measure, or simply its measure, and denoted the absolute value of E equals to its outer measure, and for measurable E. And by definition, it obvious that every open set is measurable. Here is another example. Every set of outer measure 0 is measurable. We suppose the outer measure of E is 0 and given epsilon larger than 0, and we have there is an open G containing E with the measure of E is less than the outer measure of E plus epsilon equals to epsilon, and hence the outer measure of G minus E is less or equal to the measure of G is less than epsilon. So the set of outer measure 0 is measurable. After the above simple examples, we have a better understanding of the definition. Then we come to the theorems. The first theorem is the union of a countable number of measurable sets is measurable. The proof is just similar to the example 2, and for each EK, we find a GK such that EK belongs to GK, and here we take the epsilon times 2 to the power minus k to take over the epsilon, then we will get the proof easily. Then come to next theorem about the closed set. The theorem says that every closed set F is measurable, and to prove this theorem, we need some lemma. And here are the four lemma. The first lemma said, and closed intervals are measurable. And the second says, if A and B are disjoint compact sets, then the distance A and B is larger than 0. The third says if the distance A and B is larger than 0, then the outer measure of the union of A and B equals to the outer measure of A plus the outer measure of B. And the last lemma says that compact sets are measurable. As the lemma is not the emphasis of today's project, so I will skip the proof of the lemma, and you can find the proof on the internet or do by yourself. As we have this lemma, then we back to the proof of the main theorem. We assume that E is closed, but not compact, and we define EK equals to the union of E and another set, and this set is the absolute value of X is less or equal to K, and we have the union of all EK equals to E, and for each EK is closed and bounded, so they are compact, and therefore they are measurable. And E is the union of this measurable set, so E is also measurable. Then come to the next theory about the complement. The complement of a measurable set is measurable. To prove it, we let E be measurable and set open set Gk such that E belongs to Gk and the odd measure of Gk minus E is less than 1 over K, and the complement of Gk is closed, is measurable, and we let H equals to the union of the complement of Ek, and H is also measurable, and H belongs to the complement of E, and we can write the complement of E equals to the union of H and Z, and here Z equals to the complement of E minus H, and we can see that the measure of Z is 0 because of the Z belongs to the complement of E minus the complement of Gk, and we write the complement of E in the union of two measurable subsets, so the complement of E is also measurable. And we also have theorem about the intersection. The intersection of a countable number of measurable sets is measurable. To prove it, we can have that since Ek is measurable, the complement of Ek is also measurable, and we have the complement of E equals to the union of the complement of Ek, and hence the complement of E is measurable, and E is the complement of the complement of E, so E is also measurable. Then come to today's last theorem about the difference. If E1 and E2 are both measurable, then E1 minus E2 is measurable. And we have the E1 minus E2 equals to the intersection of E1 and the complement of E2. And the complement of E2 is measurable, and the intersection of two measurable sets is measurable. So E1 minus E2 is measurable. And that's all of today's presentation. Thank you.